The Alma, or Atacama Large Millimeter Submillimeter Array, is a group of radio telescopes. Alma scientists investigate the physics of the cold universe, probe the first stars and galaxies, and directly image the formation of planets.
Is it a huge telescope?
Yes, the Alma is composed of a vast array of radio telescopes and the most powerful observatory of its kind. Alma peers into previously hidden regions of space with unprecedented sharpness, into immense clouds of gas and dust, where stars are igniting and molecules are slowly building the ingredients of life, and where young planets are taking shape around their suns.
Do they look for other planets that might have life?
They certainly do, and how they come about. Early astronomers studied what they could observe. That meant stars, planets, and other easily visible objects. The most telling secrets may lie in the darkness between them. Light arrives in a multitude of colors we can see. But visible light is only a tiny sliver of a vast electromagnetic spectrum that encompasses every kind of light known. Though astronomers have explored most of the electromagnetic spectrum, one part has been difficult to observe: a range called millimeter and submillimeter wavelength light, which represents half of the light that reaches us from distant space. The light in the millimeter and submillimeter wavelength as it comes to Earth is extremely faint.
Is that why there are so many telescopes and they need to be so big?
Yes, the design called for 66 antennas, which work together as an array.
Wow, that must be expensive.
It sure is. Each antenna costs over $5 million. Teams from North America, Europe, and East Asia split the overall cost of $1.3 billion.
Where is the telescope?
In South America, in Chile. The Atacama Desert is one of the driest deserts on Earth. Millions of years of volcanic activity have created the perfect environment for the Alma telescope, the Chaknantor Plateau, at an elevation of 16,500 feet. Because of its dryness, high altitude, clear skies, and lack of light pollution and radio interference, the Atacama is one of the best places in the world to conduct astronomical observations.
How did astronomers build Alma's huge dishes?
The dish structure weighs over 14,000 pounds, and the assembly process was nerve-wracking. After fastening the antenna to the base, they attach the reflective panels that gather the light from space. Metalworking specialists create the dish surface, which consists of 264 aluminum panels. They must fit precisely in a perfect 3D parabola. Technicians use a 5-axis machining instrument to form each of the high-grade aluminum panels. Titanium carbide drill bits are used to hollow out the interior of the panels to make them lightweight but strong. The engineers use a coordinate measurement machine to verify the perfect shape of the panels. Every surface is digitally mapped to ensure a precise fit. Just 175 light-years away, in the constellation Hydra, is a young star called TW Hydrae that may hold clues to how our solar system developed.
There's a wonderful protoplanetary disk around the star TW Hydrae. This is a unique system because it's one of the closest known to the Earth, so we can see it in the most detail.
Only 10 million years old, or 1/500th the age of our Sun, it is just starting to take shape.
We know that there's an inner hole in the disk. We think that the hole's being cleared out by a planet in formation. And with Alma, we should be able to see the gas and dust that's forming the planet.
Alma could shed light on the formation of planetary systems, giving us a better idea of how our solar system began. Quasars are believed to be the highly luminous centers of newly forming galaxies. Astronomers estimate that some quasars may have formed over 13 billion years ago.
The light takes a long time to reach us, right?
Yes, their light might just now reach Earth because of the vast distance it must travel. Similar to this depiction, supermassive black holes are believed to be at the center of some quasars. Surrounded by vast oceans of invisible gases, they might give birth to stars. Light from the distant universe reaches Alma in extremely faint waves. To capture them requires a complex suite of sensors and electronics known as the front end.
The signals that come in are extremely weak, and the front end has to be very, very sensitive in order to detect these signals and to amplify them to a high enough level that they can actually be processed.
The antenna works by collecting light which is not visible to the human eye. Light from outer space is reflected by the central mirror and directed into one of several small apertures, each leading to a receiver that is tuned to a specific frequency. In addition to observing objects that are extremely far away, Alma also helps scientists view closer neighbors.
Like the sun?
Yes, exactly. Our sun is capable of severe solar storms or coronal mass ejections, which hurl a bevy of charged particles towards Earth at 1,100 miles per second. These storms can cut power and knock out communications on Earth. Alma will help astronomers study the sun's chromosphere, a layer of gas just above the visible surface. This will give us a better understanding of solar storms. While light from the sun and other objects is received and amplified at the front end of each antenna, the back end is where the data is combined and processed for astronomers to study. The antennas are synchronized with precision using a device called an oscillator. Each antenna has its own oscillator, and they're all synced together with fiber optic cable to one central oscillator that controls the timing of the entire array. The required precision of these signals is down to the femtosecond.
Femtoseconds isn't a word that I don't think I was even familiar with before the project started. It's so short. 1,000,000 times 1,000,000 times 1,000 times smaller than a second.
In other words, the time it takes light to travel the thickness of a sheet of paper. With miles between antennas, even very small errors could ruin observations.
Boy, they must need some big computers to run the telescope.
They sure do. Processing the enormous data streams from the back end requires a custom-built supercomputer. This is the Alma correlator.
Every antenna is producing 96 gigabits per second of data, night and day. That's enough to fill up a DVD in less than a second. In a personal computer, you have 1 or 2 or sometimes 4 processors, and all the data that you're working on has to go through a processor, be worked on and manipulated, and come out the other end. In this machine, we have 128 million processors.
Built in Charlottesville, Virginia, the correlator is the most powerful supercomputer in the civilian world. At the University of Virginia's Center for Chemistry of the Universe, a team of scientists is working to understand how complex molecules form in space, an emerging science called astrochemistry. This reaction chamber recreates the extreme conditions of interstellar space.
But what you shouldn't really feel bad about are the molecules that we're putting into the chamber back there. We're not torturing them, but what we're trying to do is get them to react.
From stocks of known chemicals, they are creating new molecules.
Every line here is a new molecule. And many of these molecules that are formed have never been seen before, ever.
These astrochemists are building a database of the complex molecules they have created. They can share this knowledge with Alma astronomers to help their quest.
What we're going to be able to do now with Alma is to make chemical maps. And this could have a lot of different implications, especially for astrobiology, where we actually want to see where do the organic molecules, the molecules that make up life, where do they actually form in these regions of newly forming stars. Astrobiology might actually evolve into astrozoology or astrobotany, where we're actually studying plants and animals on other planetary systems. And it's very exciting to say that we're actually starting that first step, starting now.
What a cool job to have. What should I do if I want to work in these fields?
The Alma project is a complex scientific endeavor designed, programmed, built, and operated by a variety of well-trained professionals. These careers can be challenging, but with the potential to explore our universe like never before, we will need top-notch engineers, computer science experts, astronomers, and many other specialists. Becoming a scientist nowadays is increasingly multidisciplinary. Some of the most interesting discoveries are made by teams that use a variety of branches of science to discover novel approaches to solving problems.
Astronomy is unique in a science in that we can use it to understand where we came from.
Nature is cleverer than we are. Just when you think you know everything, you have a surprise.
Every single field you can think of, from our solar system to star formation of all masses in our galaxy and nearby galaxies, to detecting even light from the first stars that formed. I don't think there's any field of astronomy that will remain untouched by the advent of Alma.
We're ultimately looking for our origins, our roots. And so what Alma is going to be doing ultimately is searching for our roots out there among the stars.
The name Alma in Spanish means soul. What Alma is doing is looking at the soul of the stars.